Hello everyone. In our previous video we have discussed about limit points. For any element x belongs to capital X, which is a set, a subset capital A derived from a topological space capital X, then the point x belongs to capital A is called as a limit point of this capital A if every open set, let's say G be any open set, this containing X contains a point of A which is other than X, that is A intersection G minus singleton set X is not equal to empty. This we have discussed in detail in our previous video. So let's learn something more about this. The set of all limit points of A is called as derived set. That is, the set of all limit points is called as derived set. Derived set will be denoted as D of A for any subset A of X, or sometimes we write A dash also. Through example we have discussed this. So today let's learn about one important property of derived set of a topological space. Let's consider a theorem. Let capital X be a topological space. Then first one, derived set of empty is empty itself. Second one, for any two subsets AB of capital X, if A be the subset of B implies derived set of A will be the subset of derived set of B. Again, third one, derived set of A union B will be equal to derived set of A union derived set of B. These three are very important. So let's learn the proof for this. Let's derive the first one. We'll prove derived set of empty equal to empty, but we'll go for contradiction method. Okay, let's say derived set of empty not equal to empty. Then which is not equal to empty implies there will be any element, say capital X, belong to derived set of empty. Okay, where this X belongs to capital X itself. X belongs to derived set of empty. We know that derived set is the set of all limit points. This X belongs to derived set implies X is a limit point. So let's write X is a limit point of, here the set is empty, so limit point of empty. Okay, therefore by the definition we can write empty intersection any open set G minus here point X will not be equal to empty. This is by the definition of limit point. Okay, by the definition of limit point, where G be any open set. Okay, for every open set G containing X. In particular, empty intersection, let's say any open set, say capital X minus singleton set X not equal to empty. See here, capital X is there. Capital X is there. Okay, I'm considering one open set capital X because capital X is an open set containing X. But empty intersection X is empty itself, empty minus singleton set X will be equal to empty. Empty minus singleton set. Empty minus singleton set X equal to empty. This will not become true for any case. So this will leads to contradiction. This will leads to contradiction. Therefore, our assumption derived set of empty not equal to empty is not true. Derived set of empty equal to empty. This is the first part of the given theorem. Let's prove the second part. We need to consider two subsets of X, and in particular A be the subset of B. We need to prove if A be the subset of B implies derived set of A will be the subset of derived set of B. For the subset condition, let us consider one element, say X belongs to derived set of A. As you know, we refer the concept of set theory for this. As you know, if any element X belongs to A, by our solving of equation, if we get X belongs to B also, then A will be the subset of B, which is always true. If X belongs to A implies X belongs to B, then A will be the subset of B. We are going through this condition itself here. We are considering X belongs to derived set of A. By solving or by applying some conditions, we get X belongs to derived set of B. Then we'll get derived set of A will be the subset of derived set of B. Let's do all these things, okay? For this, I'm considering X belongs to derived set of A. If X belongs to derived set of A, then derived set of A is nothing but set of all limit points of A, right? So, by the definition, X is a limit point. If X is a limit point of A, then it should satisfy the condition of limit point for any open set G. That is, A intersection open set G minus singleton set X not equal to empty for every open set G containing the element X. Call this as equation 1. As we know, A is the subset of B. Therefore, A intersection G minus singleton set X. This is the subset of, in the place of X, A will write B. B intersection G minus X. A is the subset of B. So, whole term will be the subset of whole term. Call this as equation 2. From equation 1 and 2, we can write B intersection G minus singleton set X not equal to empty, because its subset is not equal to empty. Subset itself is not equal to empty implies its superset also not equal to empty only. Therefore, this is true for every open set G containing X. Containing X. So, this is the condition of limit point for B. So, X belongs to derived set of B. X belongs to derived set of B implies, so we have taken X belongs to derived set of A. We come up to X belongs to derived set of B. So, therefore, X belongs to derived set of A implies X belongs to derived set of B. Therefore, derived set of A will be the subset of derived set of B. Hence, if A be the subset of B, then derived set of A will be the subset of derived set of B. Condition. This is the second part. Let's move towards the third part. Let us consider any two subsets of X. By this we can write A will be the subset of A union B and B will be the subset of A union B, which is always true. Therefore, by the above proven result, we can write A be the subset of A union B. Derived set of A will be the subset of derived set of A union B. If A be the subset of B, then derived set of A will be the subset of derived set of B. Similarly, A be the subset of A union B here. So derived set of A will be the subset of derived set of A union B. Similarly, for this, derived set of B will be the subset of derived set of A union B. So, considering the union of these two, derived set of A union derived set of B will be the subset of derived set of A union B union derived set of A union B. It's the same itself, derived set of A union B. Call this as equation 3. Okay, now see here, we need to prove is derived set of A union B equal to derived set of A union derived set of B. We got derived set of A union B is a subset of derived set of A union B. Now we need equality, implies now we need to prove derived set of A union B will be the subset of derived set of A union derived set of B. That is a reverse condition. Let's prove this by reverse condition. Let's consider X does not belong to derived set of A union derived set of B. In union, X doesn't belongs, which implies X does not belongs to derived set of A and X does not belongs to derived set of B. If any one set containing X implies X belongs to, so that doesn't hold. So we are considering in both the cases derived set of A and derived set of B, both are not containing X. X does not belongs to derived set of A implies X is not a limit point of A. Similarly, X does not belongs to derived set of B implies X is not a limit point of B. Right? Derived set of any set is nothing but set of all limit points. So not belongs implies not a limit point. Therefore, there exists an open set. I am considering G. Okay, I am considering G containing X such that by the definition G intersection A minus singleton set X, if it is a limit point, then it will not equal to empty. If it is not a limit point, then it will become equal to empty. Similarly, there exists an open set. I am considering one more open set H containing X such that H intersection for B, I am considering B minus singleton set X. This is also not a limit point, so equal to empty. Which implies now I need to combine these two because I need for A as well as B. Right? Okay. H intersection, combining these two, H intersection G intersection A, H of this minus singleton set X is equal to H intersection, the value of this is empty, which is equal to empty. Similarly, I will apply G for this, that is G intersection H intersection B minus singleton set X is equal to G intersection empty, which is also equal to empty. Since H and G are open sets, both are containing X, right? This is by the definition we have taken. Therefore, H intersection G, its intersection is also an open set. H and G both are open sets. So H intersection G is also open set. Both are containing X implies H intersection G also containing X. Also, now I am considering H intersection G intersection derived set of A union B we need. So I am considering A union B minus singleton set X. What required is any open set intersection derived set of A union B condition we need. So for A union B set I am considering, instead of A, here I have written A, no? So instead of A we need A union B. Instead of G we need, that is open set, H intersection G, combining these two. Okay, now this will be equal to, let's simplify all these things, H intersection G intersection, I'm splitting this. Okay, A union B minus singleton set X. I'm splitting this. A minus singleton set X union B minus singleton set X. Let's simplify again this H intersection G as it is. See here, this intersection, this union this, which is in the form A intersection B union C. A, in the place of A we have H intersection G, intersection B, in the place of B we have A minus singleton set X, union C, in the place of C we have B minus singleton set X. Right, so by distributive property this can be written as A intersection B union A intersection C. So let's apply this. Okay, in the place of A we have this intersection A. Okay, B, in the place of B we have A minus singleton set X. Okay, this is one term. Here union, in the place of A again we have H intersection G minus, in the place of C we have B minus singleton set X. Now this can be written as H intersection G minus intersection A minus singleton set X, which is H intersection G intersection is there. So by associative property we can write H intersection G intersection this, that is, which is in the form H intersection G intersection, we'll consider this as something say P. Here this is there, like this we have, by associative property we can write this as a singleton. Okay, H intersection G intersection A minus singleton set X. Okay, union, here we can write, here is intersection, right? We can write H intersection G intersection B minus singleton set X. H intersection G intersection A minus singleton set X is nothing but empty. Union H intersection G. Again by applying commutative property we can interchange this G intersection H. So now we left with G intersection H minus H intersection B minus singleton set X. Right, H intersection B minus singleton set X is empty, so it will become G intersection empty. H intersection empty is empty itself, union G intersection empty is empty itself, empty union empty is empty itself. Therefore we got the condition H intersection G, this is an open set, intersection this minus singleton set X equal to empty. We got this condition. This is one of the open set and this is A union B, which is equal to empty. Right, implies A union B, for A union B we have written, right? So X is not a limit point of A union B. X is not a limit point of A union B implies X does not belongs to derived set of A union B. So we have taken X does not belongs to derived set of A union derived set of B. We came up to X does not belongs to derived set of A union B. By this we can write derived set of A union B will be the subset of derived set of A union derived set of B. Call this as equation 4. Therefore, from equation 3 and 4, in case of 3 we have proved the reverse condition, right? So from 3 and 4 we can write a derived set of A union B equal to derived set of A union derived set of B. Okay, like this we prove the result. In the reverse case, this will be the subset of this, that we need to remember. That was the video. Let's come with one more topic in my next video.